BGS, British Geological Survey. And I'll provide an overview on radon as an hazard. I'll try to address 5 different aspects of radon, namely, what is radon? Why is radon a radiologic health concern? A bit about radon mapping in the UK, current options to reduce radon levels in homes, and radon in West Midlands. What is radon? Radon is a chemical element, gas, that sits in the right bottom end corner of the periodic table. It's noble, it's heavy, it's radioactive, and it's geogenic. This set of characteristics makes radon a distinctive element. Its natural behavior is driven by physics more than chemistry, as it tends to not combine with other elements, not even with itself. Noble gas means that it is very low chemically reactivity. Heavy means, in this case, it's 7.5 times denser than air, so it tends to sink in the absence of air movement. Radioactive, it's because its nucleus is unstable, emitting ionizing radiation, and geogenic, as it is produced in rocks and soil minerals. What can I? Radon has 3 naturally occurring isotopes directly produced from radium in 3 different radioactive decay chains. Radon-222, with a half-life of 3.82 days, is produced from radium-226 in the radioactive decay chain of uranium-238. The other 2 isotopes, they are, the first is less than 1 minute, the half-life, and the second one is its half-life is less than 4 seconds. The 3 series are made of solid elements, solid isotopes, except radon, which is a gas. And they all end up in stable lead, in a stable lead isotope. Radon-222 shows the highest radiologic concern of the 3, as its half-life is long enough to allow it to move away from the source and accumulate in confined spaces. When it's said that radon is geogenic, there are 2 concepts related with geology to keep in mind. It's the source and the pathways. The source, because radon is permanently produced from uranium in rocks and soil minerals. Uranium can be found in small quantities in all types of minerals, including the most common ones, such as quartz, feldspar, mica, calcite, etc. In magmas, it tends to concentrate in the late stages of crystallization in accessory minerals, such as zircon and allanite, and uranium minerals, because its size makes it incompatible. In the surface environment, it often shows high mobility. It may bond with organic matter, clay minerals, and crop precipitate with phosphates and some iron oxides. So we may expect radon emanating from almost any mineral and exhaling from all kinds of rocks and soils, but of course, with higher rates for uranium-rich rocks. High concentrations of uranium may occur associated with some specific rock types, such as uranium ores, of course, but also most of granites, black shales, phosphate rocks, some sandstones, and some limestones. The pathways relate with permeability of rocks and soil, such as connected pores, cracks, fractures, faults, geological limits, etc. And carrier fluids, such as groundwater and CO2. Permeability and carrier fluids will allow radon gas to travel within rocks, laterally and upwards to the topmost geological layer, the soil, where it may accumulate. While in the soil, the pathways of radon gas complicate as it becomes sensitive to weather conditions. Radon outdoors quickly disperses down to harmless levels, while concentrating in confined spaces such as mines and caves, but also in buildings. Radon gets into buildings by diffusion, following a difference in concentration. This is because radon in soil air is several orders of magnitude higher than in air. And also by advection, following a difference in pressure and temperature. Typically, there's lower pressure and higher temperature indoors. These physical phenomena force radon from soil air entering buildings through gaps and cracks and joints in the floor. In the UK, radon indoors averages around 20 becquerels per cubic meter, but levels above 10,000 becquerels per cubic meter have already been measured. Typically, basements and cellars show the highest levels, followed by ground floors. Indoor radon varies with time, as weather does. So why is radon a radiologic health concern? Radiation from indoor radon alone accounts for about as much as the sum of all the other types of radiation a person is subjected to in the UK. Also, radon can cause lung cancer. As we breathe in, radon and its radioactive decay products enter the lungs. Radon itself tends to follow the breathe-in, breathe-out movement, while its decay products more likely attach to the lungs tissue as they are solid and chemically active. These decay products, namely polonium isotopes, are extremely radioactive, keeping emitting alpha radiation in the lungs. This may cause localized damage, potentially generating lung cancer. Radon is the second cause for premature deaths by lung cancer, right after smoking at world level. In the UK, it is estimated that about 1,100 deaths by lung cancer per year are caused by radon inhalation. This is 3 to 4% of all deaths by lung cancer. So radon is perhaps the deadliest geological hazard in the UK and maybe in many parts of the world. How do we deal with radon mapping in the UK? And why mapping radon after all? A radon map provides basic information where indoor radon is likely to be high. Those areas are defined as radon-prone areas, and this allows us to prioritize remediation and prevention to hold and new buildings in radon-prone areas, with the ultimate goal of decreasing the number of deaths caused by indoor radon. A joint between UKHSA and BGS was established more than 20 years ago to develop methods, produce and deliver radon maps for the UK. The idea behind joining UKHSA data with BGS data is quite simple. Combining indoor radon measurements and mapped geology provides a better model than radon maps using indoor radon measurements alone or maps using geology alone, which was the case in the 90s. As seen some slides before, rocks and soil are both the source for radon gas and can also act as a pathway for it in a complicated relationship. Radon measurements, on the other side, taken in our homes, show us whether and where we are being exposed to radon. And from these measurements, we can work out where people are receptors to radon gas. Typically, when discussing any type of hazard or contamination in our environment, we need to identify a source, a pathway, and a receptor relationship in order to establish that a hazard or risk is present. The combination of the two sets of data from UKHSA and BGS allows us to do that. Also, we can use our knowledge of geology to constrain the sampling bias of measurements, because we know, in fact, more radon measurements are taken in areas where high radon levels is already known, and geology can also provide estimates for areas with poor coverage of indoor radon measurements. In fact, it's ideal for locations where nobody lives yet. We are about to release the new edition of the radon map for the UK. This will be the 1st of December. The new edition is published some years after the original, and so not surprisingly, some changes to the number of measurements, to the geology, and to the method for map production took place in some extent. Changes which we expect to result in a better radon map. For the new edition, the number of radon measurements increased 17%. We have 80,000 more radon measurements. And the geology map is 5 versions after the original. I'll show you a bit more in the next slide. Some changes in the method have been applied, aiming at obtaining a more robust radon map. The new edition makes use of 4 levels of geological complexity. We call those BS, BED, LEX, and RCS, contrary to the single level of complexity, the so-called COM, with a layer of higher complexity, BS, providing more detail than the original COM. These 4 layers of geological complexity allowed us to use a single gridding method across areas with less than 30 measurements, and to ensure a minimum of 10 radon measurements per simplified geology, minimizing the use of expert judgment, something that was not possible to achieve in the previous edition. The geology doesn't change much in Great Britain, of course. However, how we map it and our understanding about it is evolving all the time. In the last 15 years, the vast majority of our geology map has had some form of update or resurvey. And it is that improvement of data that impacts how much we understand how rocks and soil behave. In the map shown in this slide, only the dark gray areas are completely unchanged since 2007, the date of the release of the first radon map. The green and blue areas are completely new maps, some of which in areas where radon can pose a risk. Pale gray areas are where minor changes in nomenclature have been made. Better maps and faster computers allows us to do more than we could in 2007. So revisiting how we combine areas of geology to use together with the UK HSA measurements is a logical next step in improving the mapping of radon. The level of complexity of the 4 simplified geology layers can be observed in the 4 frames. They all look similar, but on closer inspection, there is much finer detail in the leftmost groupings and decreasing detail and spatial clustering towards the right. A hierarchical structure exists between them, such that bed, the second map, is a generalization of BS, the first map, after removing the superficial units, while LEX and RCS, the third and the fourth, are chronostratigraphical and lithological generalizations of the second one, bed. Each layer offers different opportunities to statistically analyze the UK HSA measurements. Preference was given to the geological set of codes with higher complexity, the BS on the left, as it combines information from bedrock and superficial cover. UK HSA computed the radon potential, making use of the more complex geological codes, the BS, for which 30 or more indoor radon measurements were available. PGS computed the radon potential for the remaining BS geologies, that is, those with less than 30 measurements. And where necessary, a lower level of geological complexity was used to ensure a minimum of 10 radon measurements per grouping. Most of Great Britain was mapped by the UK HSA, about 75%. That is, there were at least 30 radon measurements in enough BS codes to cover 3/4 of Great Britain area. For these areas, the estimated radon potential varies within and between geologies, the BS codes. The remaining areas, about 1/4 of Great Britain, were mapped by the BGS, the gray bits on the map, which correspond mostly to the less populated areas. For these areas, the estimated radon potential varies between geologies, but not within, because due to the low number of radon measurements in these areas, only one radon potential value was computed for each simplified geology. Now I'll show you the data computed by the BGS in 4 frames. The BS geologies with less than 30 measurements were processed by the BGS in 4 steps according to the number of measurements in successively less detailed simplified geologies. On the left, you can see the coverage of BS geologies with a number of radon measurements between 10 and 30, and this covers about 8.8% of Great Britain. On the right, when a BS geology has less than 10 measurements, we use the following layer of geological detail, bed, if its number of measurements is 10 at least. 12.1% of Great Britain has been covered by this one. Now, on the left, when a bed simplified geology had less than 10 measurements, we use the following layer of geological detail, LEX. If its number of radon measurements is 10 at least, 2.6% of grid pattern has been covered. And finally, on the right, when a LEX simplified geology had less than 10 measurements, we use RCS instead. If its number of radon measurements is 10 at least, only less than 1% of Great Britain has been covered. All these 4 frames are based on statistics of all the radon measurements in the respective simplified geology. One radon potential only has been determined for its simplified geology. Finally, we merged the five radon potential frames, the one made by the UK HSA and the 4 made by the BGS, which cover 100% of Great Britain. Then we split the radon potential in 6 radon classes, and then we add a buffer of 25 meters to the higher classes over the lower classes, and choose a color palette to show the final radon map. What are the current options to reduce radon levels in homes? So we have a problem, but there's a solution also. Radon levels in existing homes can be reduced by applying one or more of the 4 options according to floor type and radon level. All this information is available in UK Radon, a web page dedicated to radon indoors. The positive ventilation forces fresh air into the room, diluting radon and fighting radon to come up from the ground. The active radon sump is installed outside house, aiming at reducing the air pressure underneath the building. The natural underflow ventilation works in buildings with suspended floor. The mechanical underfloor ventilation helps increasing the ventilation under the suspended floor type of buildings. And finally, the airtight membrane can be applied to new homes to prevent radon seeping from the ground underneath. Radon protection is part of building regulations, namely for new houses. And several rules are applied according to the country. The so-called basic or full. They are applied according to the radon potential of the area and as defined by the building regulations in place for each one of the 4 countries. Finally, a bit about radon in West Midlands. Here you can see the level of detail of geology combinations, the BS on the top left corner, bed below it, the LEX, the RCS, and the coverage. Each of them was used to compute the radon potential and radon class in West Midlands. You can see that the percentage covered by each one of the 5 gridding methods in West Midlands is relatively similar to the national coverages, namely 77.4% of the area, slightly more than 3/4, showing BS simplified geologies with 30 or more radon measurements. The dark green in the map on the right. We have more than 99,000 measurements in West Midlands and more than 700 BS simplified geologies have been used. On the left, you can see the old indicative radon map, and on the right is a blurry new indicative radon map. Sorry, the release is only on the 1st of December. The new shows the same pattern, although generally slightly more extensive in some cases. About 52 remains the same maximum radon class, and 31 changes one class only. Less than 20% of the West Midland map will see a change of 2 or more maximum radon classes. If you compare the two maps, although one is blurred, you'll see that the highest classes are located in the same areas, and they relate with a few types of rocks. Some of them, like I can mention them, it's the Carboniferous coal measures and some other rocks. For instance, in the top right corner of the map, it's already related with the hotspot around the Peak District. The Silurian rocks, namely Ludlow, but also Pridoli and Venlock in the southwest quadrant of the map. You can see them, some hotspots there. And the Lias, inferior oolite and great oolite groups in the southeastern part of the map. These are among the rocks over which we find higher radon levels in West Midlands. And that's it. So I'm ready for some questions, if some.
Thank you very much. That was very interesting, and I'm looking forward to using the new radon box, especially the amount of detail that's portrayed there. First question, I guess. How many people have been involved in the development of these new maps, and how long has it taken?
So this is a partnership between UKHSA and BGS, and yes, there's a group of people. Usually some 4 from UKHSA and 3 to 4 in the BGS. And yeah, they take care of the indoor radon measurements. They have a huge amount of radon measurements, perhaps the largest collection in the world, at least held centrally, because this is important. When you try to put something like this together, it's better if the data is managed centrally. So that's a good thing about the UK HSA measurements, and also about the geology, of course, because BGS take care of the geology bit. And so we start. It's a long process. We have been working on this perhaps 4 years or something like that, because we've started with some exercises in the southwest to see what changes should be applied to the new map, and to think about if we should change a bit in the methodology used to produce the map, because we knew already that we would have more measurements, and of course the geology have also changed our understanding about it. So we knew that eventually it would be a good idea to remap radon somehow. So yeah, that's a lot of people involved. And the team has changed since 2007. So there was, let's say, we all had to learn a bit from our predecessors, namely John Miles from UKHSA and Don Appleton from PGS. We had to learn from them to see what they were doing and then try to apply that or apply slightly better methods.
Brilliant, thank you.
I don't know. Yeah.
Sorry. Do we have any other questions?
Yes. Adrian Collins, I'd like to ask a question about whether the phosphate deposits within the chalk have been included in your survey, because I'm aware of issues, particularly relating to the Stonehenge tunnel.
Yeah, we know that phosphate rocks are rich in uranium, but sometimes if the rocks on top of it somehow may be a barrier upwards, but there may be some pathways laterally, for instance. And sometimes you have this type of rocks, and in fact, the radon gas will end up showing where it travels to, you know? So it may use, for instance, the limestones as a good pathway because of the caves, because it's a very characteristic type of underground, which allows radon to flow to the caves. And yeah, so that may be the case. So in when you have high uranium levels in some rocks, and these are in contact with rocks which are very permeable, then the radon levels may show high in homes relatively far from that spot, for instance, if that's the case. But of course, if those rocks are outcropping, then of course they will be a source itself to radon in buildings.
I'm aware of two areas where there's phosphate deposits in the chalk close to the surface, which may pose a hazard. One is in northwest London, the other is a Stonehenge tunnel. So it's a question whether there's any monitoring there to verify the hazard.
I'm not aware of that monitoring.
Yeah, I thought that was the case, but I just thought I'd raise it because phosphate in the chalk is a source, and I think it should be monitored.
Yeah, it makes sense what you're saying. Yeah,
I have more data.
But of course,
I have more data to provide. I have more data I could help you with if you need, particularly in northwest London.
Okay, I'm not currently doing monitoring, but it's something perhaps to talk with our partners, because usually what we measure, what our partners measure, to be more precise, is radon indoors in houses. And so yeah, eventually that type of works may end up may end up creating hotspots in some areas, perhaps. I don't know. Yeah,
Well,
that
for the
may be
Stonehenge
possible.
for the Stonehenge tunnel, I did raise it as a health and safety issue for the construction of it, if and when it ever happens. But I'm not directly involved with the project.
Okay. Perhaps you can email me and I'll try to forward to people that eventually can do that job. I don't know.
Thank you.
You're welcome.
Antonio, thank you for a very interesting talk. I don't, unlike Adrian beforehand, I don't have much in the way of knowledge on this, but I did notice that, which is something that surprised me. Yeah, we saw the hotspots of radon where you've got the igneous centers, particularly the acidic rocks. But I did notice this line going from the southwest to the northeast, which I'm now following the conversation, is probably the Lias Jurassic rocks, and which surprised me a lot. And is that simply because they're acting as conduits from a source? And in which case, how far do you think the radon can travel?
Yeah, I understand your question. In this case, you know, limestones can also act as a source, not the rocks themselves, but we all know that limestones tend to weather much faster than other rocks. And this means that even if the rocks themselves have low levels in the minerals, because those minerals are washed away, then radon may, how can I say, uranium may concentrate in the sediments in the caves and in the walls, for instance.
Right.
And that may help explaining a bit that line. Yeah.
Yeah.
This could be the case. Yeah.
Yeah. Okay. Yeah. Well, that kind of makes some sense, because I do know on logs, uranium is always been associated with faults. So that makes kind of sense what you're saying.
Yeah. Yeah. It's not the mineral of the rock itself that has high contents in uranium. It's the sediments that are derived from those rocks, which are much faster growing than in other types of rocks. So yeah, and then they end up in caves, basically, don't they? And on the walls of the caves.
Yeah.
And that may increase the radon flowing in those caves. Yeah.
Brilliant. Well, thank you. That helped a lot. Thank you. Very good.
You're welcome.
Hi, Andrew, have you your hand up?
Yeah, I wonder if I just might make a comment. One of my other hats is effectively to do with house retrofits and the like. And one of the things that immediately concerned me, I know the current building regulations are very strict on new builds, but they don't necessarily get adhered to, shall we say, by DIYers and housing insulation specialists who probably aren't aware of the gross danger here. So, I mean, I'm just making the comment that this has really brought this to the forefront of my concerns now for any retrofits that I advise on going forwards, because it's obviously really important that if you're reducing the airflows through properties in order to make them warmer, that you make sure you ventilate properly as well, to ensure that this radon risk is minimized.
Yeah, and it's something that is coming out now. because the effect is opposite, isn't it? Or at least that's what we all think. But fortunately, the radon maps are based on indoor radon measurements before this kind of protection, hopefully. So perhaps in the future, we'll have to, you know, to produce these maps, we better rely on houses which don't have this kind of problems, so we can keep spotting the areas where radon should be addressed. I know this doesn't answer totally to your concern, but there's only one thing that we are sure about, which is radon. You can only know if you have radon in your home if you measure it, if you analyze the house. Because if you think, even if you are in class 1 radon area, which is basically an area where radon levels are low, we still have, let's say, it's up to 1% of the houses may still have high radon, and that means 10 in 1,000 houses. Not much, but it can be mine. So I would measure it. You know what I mean? Yeah, it's a work in progress. I think UKGSA, our partners, they are concerned about all these discussions around energy efficiency and how it may affect radon levels in homes. But of course, this is all a matter of working on it. It's something relatively new. And
I just wonder if it could be built into the current sort of past 2035 regulations in a renewal of that, so that you actually have to do a radon test prior to doing anything and afterwards to prove that you haven't made things worse. You know, even if you just put notices up in every DIY store that says, "Don't forget radon's a hidden killer," and do something about it. It's getting it more into the public eye, because it clearly is a very important risk to bear in mind for housing.
Yeah, that's right. For instance, houses that have a basement, even if they are in a class 1 radon, they all are considered of higher risk because they have a basement, and in basements you have not only the floor but also the walls in contact with the soil, and so usually the radon levels are higher. So these are the exception. When you have a house with a basement, it really doesn't matter if it is in a class 1 area. It should be at least measured. It should be measured, at least the basement. And those kind of rules exist. So hopefully we could also address your question with as an exception or something. I don't know. Yeah.
Okay, do we have any further questions? Okay, there's nothing in the chat. I think that's it. So thank you very much. Seb, do you have anything to add?
I just wanted to say thanks very much, Antonio. It was a very interesting talk. And yeah, thank you. And just to let people know, next month we've got Professor Tim Elliott from Bristol University to talk to us about the elemental composition of the Earth. See you then.
Thanks, Antonio.
Right. Bye. Cheers.
Cheers.
Thank you.
Bye bye.
Many thanks.
Bye.
How do I leave this?
Should be a red button in the bottom right that says end or leave.
Yeah, I'm trying to. I can't find it.
Hmm.
Oh. Should be somewhere. I didn't find it yet.
You might
What can
have
it
two
be?
screens. There might be two screens
I
open.
have
to
two
see.
screens, yes.
Yeah, it's on one of them
Oh, it may be there. Yeah.
with all the
Okay,
names.
I can see leave now.
see.
All right. I'm gonna leave then.
Brilliant.
Okay.
Thanks
Thanks
again.
very much.
Okay.
Thank you.
Cheers. Bye.
Good night.
Bye-bye.
Bye.